Today we are going to start with the spring and damper elements. Okay. What is that? We have a problem. Compute. Okay. Damper elements. What is the spring element? Hacer. Anyone knows? What is spring? First of all, we need to talk about the modeling elements containing elasticity. What is elasticity? What is elasticity? Red guy, Ferrari. What is elasticity? You not know? I think. Okay. In the second place, we need to talk about the modeling elements containing damper. Hacer, what is damper? Okay. And after that, we drive the what? Equation of motion. Of MCK. Okay? Mass spring damper system. Okay? These are the objectives for today. And so, let's take this one. What's your name? In front of? Yes. Huh? Beyza. Beyza. We have three kinds of energy, Beyza. First of all, we preserve, Beyza, preserving, we storing in universe, and also we losing. Which components store the energy? Spring, damper, or mass? Which one? Spring, right? And so spring store the energy, and so it's a potential energy. Okay. And so what is used to be lost in energy? Huh? Yes, damping. And so what is preserved energy? Just remember the Newton's law. Motion, but which elements? There is one part to be left in here, which is equals to the what? Mass, right? This is kinetic energy, this is potential energy, and this is the loss energy. Okay. And so if you have a system only containing the preserving or storing energy, we don't have any loss in here, and so kinetic energy plus potential energy must be equals to the what? Some constant. Just remember the previous lesson, we have talked about the equivalent inertia and the mass factor, right? And so in the previous lesson we derived to what? The equation of motion based on this information. But in this case, we will add the one more item, which is called damper or the damping, right? So, in order to do that, we need to give the sum title for that one spring element. Okay? What is spring element? Spring, just like the spring in the physical world, right? We have it. Have everybody see the spring in real life? Okay. And so I can write this form in here just like this one. Some physical objects are not rigid. What's the meaning of the rigid? Yes, it deforms under to what? The force or torque or pressure, right? And so we can write easily that are not rigid, and then force, torque, pressure are applied to what? To deform these objects. Okay, and so if it deforms, and so we can contain the energy coming from the what? The force, torque, and the pressure values. Okay, you understand that? What's your name? Emre. Okay, so but we need to write this form, and it returns to the what? To the original shape of itself without actions, right? What's the meaning of action? Action is force, torque, and pressure, right? And so it returns to the what? Original shape, which means that if we push this item or the body, and then this body deforms, and this deforms contains what? Or storing the energy. And so if I push the what? Push out the force, torque, and the pressure, and so this deformation is recorrected by the shape, and so it contains the energy, and after that it releases this energy, which is called the spring element. Okay. But in modeling techniques, we can write that, we can model it just like this one. We have the K value in here, and so we have the some points to what? To end of these terms. Okay, and so if we apply the F force in here, and then we can write that the X is the deflection rate of these terms, and so this X is the deflection. Okay, so if we push the K spring in here in the direction of the right, and so this X is increased, and so in proportional with this the increasing in the X, and so this K spring contains or the store to the energy, potential energy or storing energy in here. Okay, and also we may have to what? To L in here, free length. In real life, just remember that we have a free length in the what? In the spring, right? And so this K is coming from the what? It could be anything. Okay, which means that K must be a spring, but I can model this t-shirt as the what? Sweatshirt as a spring, right? Because I can push, and if I release and see, it returns to the what? To the initial position. The human can also be modeled by a spring. The heart can also be modeled by a spring. The muscle can also be modeled by a spring. Because if I push this one, and so these muscles deflected in terms of this one, because I push my hand, and so if I release my hand, and so this muscle returns to what? The original position. Okay? And so where is it coming from? The basis of these terms is simple. Just remember the material science lesson. We have the sigma and epsilon value. What is the sigma? Strange, right? What is the epsilon values? Strain, yes? And so, just remember that we have the sum pattern in here. We have the linear region in here, just like this one. After that, this is the elasticity, and so we have this kind of properties. This is the plastic deformation, this is the elastic deformation, right? And so, if I apply the sum strength on this material, any material, and so we can create the linear elasticity in here with the rate of the sigma and epsilon. Just see that this rate at always to what? Constant, right? Which means that this elasticity value is sigma divided by epsilon are always constant at what? At the linear deformation, right? See? You understand that? Okay? So, after that, we can write the formula. The formula is to what? The force value is equals to K times X. Okay? This is the Newton. And so this K is equals to what? The Newton divided by M. Okay? See? These are the formula. Because this is F is a force, this is the X. Just like the what? Just like the sigma equals to elasticity rate and epsilon value. Right? We have the analogy in here. And so, we can roll to what? To this kind of information. Here we have the spring factor, and we can push to what? The F, or just remember in the real life applications, we can compress or extend, lengthening this K, and in other way we have storing energy in here. Okay, just like this one. Any question? Okay. And so 4.1.3 analytical description of spring factor. Suppose that we have suppose that we have cylindrical rod like this one. We have the area of the A, and we push the F in here, and also we can define the initial length of these terms in here. Okay? And so if we push this rod to the right direction, and then it deforms. But we must say that we have the elasticity value is constant because we have the linear deformation in here. Otherwise we have a plastic. This body cannot return to the original position. Okay? So how we can analyze this value? Just see that we have this information, sigma divided by epsilon is equals to the elasticity. And so I can take this equation just like this one, and so what is the strength value? F divided by A, right? This is the pressure. And what is the epsilon value in here? Yes, elongation X divided by L, right? And so we can equalize these terms is equals to what? The E. And then we can write it F divided by A, E times X divided by L, right? And also we can reorganize this equation, E A X divided by L, or E L times X, right? And so, what is the K value right now in this equation? Yes. See, this is coming from the what? This notation. This K is equals to the what? The material properties, which is called the what? The elasticity and area of this cylindrical rod for obtaining the pressure values. And so also we have the initial length values in here, right? The idea is simple. See? This is the what? This is the translational property. Also, rotational property is not different with this one. In the book, check the table 4.1.1, okay, and 4.1.2, okay. Please check it in the book, Palm book, okay. So, if you obtain this spring factor, and so we should drive the what? The just like the resistance value, series and parallel elements can be added in here. Just remember the what? The electrical circuits. If we have the parallel resistance, and so we add the resistance, or we take the inverse value of this term. Which one is true? In the parallel. But in the series, on an electrical circuit, sum, yes. And so, just like the resistance, this K, or the spring factor, can be combined into the what? Into the serial and the parallel equivalent spring factor. Just like the what? Equivalent mass and inertia. Okay? And so, in this case, we have two conditions. Suppose that we have two conditions. Just like this one. For example, if we have the X value in here, and so the F see K1 and K2, and also X, F, K1 and K2. One of them is parallel, one of them is series. The formula is the same. If force is applied to both elements at the same time, it is parallel. This is our rule, okay? In this case, if we apply the F, both K1 and K2 is affected by the F. But in the second place, just see that this is not the case, because in the first place, F is applied to K1 and K1 pushed to K2. And then this is the serial, right? This is the basic rule. And so, how we can do that? And so, the generated F must be equalized to what? The F1 plus F2 in here. And also, we can write these values just like this one, K1x plus K2x, right? This is the formula. And so, if we have the any parallel spring, and so we can sum it with each other. But in the serial notation, if the force not applied at the same time, right? Do you understand that? Because F pushed to K1 and K1 pushed to K2 in here. This is called serial. Okay? In this case, we need to write that the x f divided by k plus 1 and f k plus f divided by k2. Okay? This is our equation. One of them is that one, the other one is that one. Okay? And so the f is equals to the what, or not the f, the x is equals to what, f times 1 divided by k1 plus 1 divided by k2. Okay? And so k equivalent value is coming from the what, the 1 divided by k1, 1 divided by k2 over minus 1. In the what? In the serial connection. This is the key equal. But in the what? In the parallel. This is what? This is the serial. Okay? Do you understand that? Okay. If this is the case, and then we can write to the what? To the examples. Determine key value for a given system. F K K K K K. Okay? And this is the wall. How we can calculate the key equivalent K values in here? How we can do that? For the solution, we can write that first of all, this must be collected in here. This serial or what? Serial. And so key 1e is equals to what? The 1 divided by k plus 1 divided by k over minus 1. And so this is equals to k divided by 2. Okay? This is the first solution. And the other one is equals to the what? Okay. And so k is equals to what? The k2 and is equals to the what? The 3k. Right? Because it's parallel. So this picture is to what? Is k divided by 2 times 3k and its wall. And so after that we have to what? Serial or the parallel connection in here. Huh? Serial. And so if this is the serial, and so the key A, which is equals to what? 1 divided by k divided by 2 plus 1 divided by 3k over minus 1. And so 3.2 3k plus 1 divided by 3k over minus 1. 3k 7. This is equals to what? Our equivalent spring factor, which is given in our system. Okay? Any question? If you don't have any question, and so we will continue with the 4.2.3 and the effect of gravity. What is the effect of gravity? In order to define it, we just write the two conditions in here. Suppose that we have mass with inclined trajectory, just like this one. So if we have any spring factor in here, m and k, and so we have the free length in here, L, and the center of gravity rate with the A, and also we have the G in here, okay, with the inclined trajectory. And so if we let the object slide, and then we have this shape in here. It's the wall, this is the phi, and also this one, m, and then we have the initial length just like this one, L, but we have some deflection rate in here, sigma st, and also we have one more a parameters in here in this case, because we let the object to slide on this page, and so this k what sliding, and so stopping some points, okay. And so if we have this information, and then what is the values of this force mg times sinus phi, and so we can easily write that m times g times sinus phi minus k times st is equals to 0, okay. This is what? This is the R force, or the reaction force to the what, to balance this system at this point, right? Otherwise we should move. See, you get it? Do you understand that, everyone? Any question? So from this point we can conclude that m times g times sinus phi divided by sigma st can be used to calculate the k constant values, okay. It can be defined and it can be found just like this one, right? Any question? But in the dynamics, this is a constant value, right? If we define the new parameters just like the x deflection in here, we can write this equation mx dot dot, just using the Newton's law. We have a force just like the pendulum system, right? And so if this is the equals to what, minus k times x plus sigma st value, because if we push this force just like this one, and so the k must always in the reverse direction, this must be equals to the what, the minus, but our force m times g times sinus phi must be equals to the what, in the right direction, because we have the f in this direction, right? Right? Okay? Everyone understand that? If this is the case, just remember that we have this formula, right? K times sigma st is equals to what, mg sinus phi, right? And so if this is the case, minus k times x plus mg sinus phi minus k sigma st, which is equals to the what, 0. And so our dynamic, we can write it, the dynamic for this case is equals to the what, m times x dot dot plus, or not plus, is equals to what, minus k times x. See, the other ones are removed from these equations, guys, okay? Everyone understand that? Which one? In this case, we have the, just remember the previous lesson, we have delta F is equals to what? Mx dot dot, right? This is the Newton's law. And so we need to write the whole the forces in here. And so we have some forces from the gravity. And also we have a forces from the what? The K, spring factor in here, right? But these forces is going to what? The downside. The K forces is upside. And so the K forces must be minus. The other one is positive, right? And so, and we know that if we take or the get free this response, let the free this mass, and so this is equals to what? To this one. And then this mg sinus phi minus k times sigma st removes to each other, and so we will have this equation in here in the dynamic form. Okay? Any question? Any question? Okay. So we need to solve this equation. Solving the equation of motion. Firstly, just remember that we have Wm values in here, k divided by m, okay, with, just remember, mx dot dot plus kx is equals to the f, right? If we apply the f to any k and m f value, we can write the r formulation in here, see? And so in the previous lessons we have obtained what? The xt is equals to what? X dot 0 divided by wn times sinus w omega n t plus x 0 times cosinus w n t, right? These are the solutions for the initial conditions. Remember that? Remember this formula? Remember? Huh? Okay, thank you. Just remember that if we take the Laplace transform of these terms, and so we have the what? The s divided by s squared plus wn formula in the definition of the natural damping ratio or the natural frequency or the damping ratio. Just remember that. And so after that we can write this formula based on these informations. Okay? So we can write it actually in S domain. We have to what? The xs multiplication ms square plus k is equals to what? The f. And so the xs is equals to what? 1 divided by ms square plus k times fs. Okay? These are the form. And after that we can write to this equation just like this one. If we divide the every part, numerator and the denominator, with the what? With the m and m, and so we will have 1 divided by m s square plus k divided by m times fs, because it must be equals to what? The unit step signals in here. Okay? So anyone knows that? Huh? Wn square. Yes, this is our solution. So if we take these values, the xt is equals to what? 1 divided by m wn square 1 minus cosinus wn t. Okay? This is the another solution for this system. Or xt is equals to 1 divided by k 1 cosinus Wn t. Okay? If you have calculation about these terms, and so these terms gives us these parameters in here. Okay? If you take the inverse Laplace transformation, we will have these formulations in here for the unit step signal. Just remember that. We don't have any initial condition in here, but we have in here, for this case, if we solve this equation, x0, x dot 0 is equals 0, okay? So, we have this formulation, and just see that xt is equals to what? 1 divided by k times 1 minus cosinus Wn t. These are the solution. Okay? This is so simple, but you need to take the inverse Laplace transformation under the what? Apply the unit step signals in here to this system. Okay? Any question? Okay. There is no question. And then we will take a break.